And here's another completely different topic, semiconductors. Semiconductors and band theory. So we've talked about metals and the electron C model of how they can conduct electricity. Band theory is a more comprehensive model. It explains metallic solids. It also explains different covalent solids. And it came out of molecular orbital theory. So molecular orbital theory, if you remember, was where we were taking an orbital from each of the atoms and we were combining them into an orbital that was shared over the entire molecule, and we get the bonding and the anti-bonding orbitals. If nothing else, I hope you at least remember a summary like that of what molecular orbital theory was. So the atomic orbitals of each of the atoms in a given crystal combine, and they are delocalized over the entire crystal. In some sense, a crystal is like a very large molecule. So a diamond, it's carbons bonded to each other. In a sense, that one diamond is one ginormous molecule, right? And so the orbitals overlap with each other and are delocalized over the entire molecule. So when the atoms combine, they form molecular orbitals. The lower energy bonding orbitals are the ones that are occupied by the valence electrons, and the anti-bonding orbitals are empty. As we get more and more atoms in this molecule, as we make our crystal bigger and bigger, the energy difference between those levels becomes negligible or completely unimportant. So here's a diagram. Here we're looking at energy going up, and here we have a representation of one lithium atom. So lithium has one valence electron, right? So here's its one valence electron in its atomic orbital. When we put two lithium atoms together and we combine the orbital from each, we get a bonding orbital and an anti-bonding orbital. We have two electrons now, one from each atom, and they're both going to go in the lower energy orbital, which is the bonding orbital, and the anti-bonding orbital is going to be empty. Add a third one in. Well, each atom had a valence electron in an orbital, in that 2s orbital. And so now we have to have three orbitals. Let's not worry about why this one is in the middle and there's only the one yellow one. We're not going to worry about that. But now we've got three electrons. We go to 4. Now we've got two bonding orbitals and two anti-bonding orbitals. And as you continue to add more and more and more, you get more and more of these molecular orbitals, and they get closer and closer and closer together in energy. And essentially what happens is they merge into bands. So there's this band called the valence band, where you have orbitals that are occupied, and you have empty orbitals that are very slightly higher in energy. Those are the anti-bonding orbitals, and they're empty. This band is called the conduction band, and this is called the valence band. So let's see if I covered what I wrote over here. So when you've got many lithium atoms, the energy levels of those molecular orbitals are so closely spaced that they actually fuse. So they just become this one band of orbitals. Half the orbitals are bonding. Those are the ones that contain the valence electrons. The other half are anti-bonding orbitals, and they're empty. Any questions about that concept? So what can happen is electrons can move from the valence band into the higher energy empty conduction band. So if we go back to this picture, this is where all the electrons are. But then we have this empty conduction band that is only a tiny bit higher in energy. And so electrons have an average energy, but some are higher energy and some are lower. And so a higher energy electron can very easily jump up into this conduction band. It might be the only electron up there. So it could move around and go anywhere it wants in that whole molecule-ish thing called a crystal. So it can move. This is like an empty road, and this is like gridlock. full of electrons, nobody can move. But you move over here, maybe into the carpool lane, or you're driving on the shoulder of the road, which you're not supposed to do. But it's empty, and you can just scoot along, okay? I didn't plan this, it's just coming out, and I don't know how it's going to end. Probably badly. So in metals, there's no gap in energy between the two bands. The electrons can easily move into the conduction band and shoot down the highway and go as far as they want. So that makes metals good conductors, because the electrons there in the conduction band can move. And this also explains thermal conductivity, or how metals conduct heat, because those mobile electrons can transport thermal energy from one part of the metal to another. So you heat up part of a metal, the atoms are going to move more, vibrate in position, but the electrons are also going to have increased kinetic energy. And because they can move into that conduction band and move around freely, they're going to take their increased kinetic energy and spread it all over the metal. And so metals conduct heat as well as electricity. Well, here we have an illustration of what happens with metals or other conductors. There's no gap between the conduction band and the valence band. In a semiconductor, you have a small energy gap here. That makes it harder for electrons from the valence band to get up into this conduction band where they can move. But it's not impossible. So semiconductors conduct a little bit, hence the name, semiconductors. The band gap is small. Insulators have a large energy gap. It's pretty much impossible for an electron to move from the valence band up into the conduction band, and so they do not conduct electricity. They insulate. Any questions? If we look at the group 4A elements, carbon, silicon, germanium, tin, and lead, and here we're going to look at diamond, we're not looking at graphite because that's different. We see there's an increase in atomic radius as you go down, and we see that the classification moves from insulator down through semiconductors and metals. And the reason for that is the difference in the band gap. Lead is a metal, it has no band gap. There's no gap between the conduction band and the valence band. Tin is also a metal, it has a very small band gap. Germanium and silicon are semiconductors. They conduct a little bit, and diamond has a band gap of 5.5 electron volts, and so that large band gap makes it an insulator. What happens is as we go down the group and the atomic radius increases, the overlap between orbitals on neighboring atoms is reduced because the atoms are getting bigger and bigger and they can't overlap as well. And so that reduces the energy difference between the bonding and the antibonding orbitals and causes the band gap to get smaller. Oh yeah, I missed this statement. The conductivity of semiconductors increases with temperature. If you heat a semiconductor, it will conduct better. And the reason for that is if you heat this up, then the electrons have higher average kinetic energy. And so more of them are able to jump this small energy gap into the conduction band. And that's one of the useful things of semiconductors is their conductivity is dependent on the temperature. So you can use them as a temperature probe. Because as it gets warmer and warmer, it conducts better, and you can measure the conduction. Another way to control the conductivity of semiconductors is by doping. What do you think of when you hear the word dope? Drugs? Or a stupid idiot, right? Lance Armstrong. So doping in general refers to adding some other substance in, right? So you're taking a drug to enhance your performance, or in this case, doping a semiconductor, we're adding small amounts of impurities that are going to either result in extra electrons that will be in the conduction band, or it results in electron holes in the valence band. And so there are two different types of semiconductors. An N-type semiconductor has extra electrons. So silicon is a semiconductor. Silicon is in group 4A. How many valence electrons does it have? 4. So if we mix a little bit of phosphorus with the silicon, how many valence electrons does each phosphorus atom have? 5. So when we stick some phosphorus atoms in there, where does that 5th electron have to go? It has to go into the conduction band. The valence band's full. The conduction band is just a little bit higher, and so adding the phosphorus will cause there to be some electrons that are always present in the conduction band, and so it's going to conduct electricity better. The more you put in there, the more it's going to conduct. So those extra electrons go in the conduction band. They're mobile. They can conduct electrical charge. So it's called an N-type semiconductor because the charge carriers are negative. Negative N-type, negatively charged electrons. Another way to dope a semiconductor is to use an element that has fewer valence electrons. So we can dope silicon that has 4 valence electrons with gallium. Gallium only has 3 valence electrons. So now you're going to have some empty holes in the valence band. When there are holes there, that allows electrons to move from where they were to the hole next door. And then that opens up a hole behind them, and the previous electron can move in. And so that allows for conduction because the electrons can move between the holes, or you can think of the hole as being a positive charge. It's the absence of the electron. And so these are called P-type semiconductors because the hole acts as a positive charge that can move. Any questions? So silicon chips have millions of p-n junctions. And these are at the heart of most electronic devices. Without silicon chips, we wouldn't have the iPad or this screen or just all kinds of stuff we wouldn't have. The p-n junctions are tiny spots that are p-type on one side and n-type on the other. And you can make all kinds of cool stuff out of these. They can act as diodes. A diode is something that allows current to flow in one direction only. Or you can make amplifiers out of them that will take a very small current and amplify it into a larger current. They're useful for all sorts of things. Any questions? So which element would you dope into germanium to create a p-type semiconductor? So p-type means we have positive holes that can move. How do we get holes in the valence band? Less electrons, right? So we're looking for something with fewer electrons. How many valence electrons does germanium have? 4. So it's in group 4. So we have 4 valence electrons. So we want something with fewer. How many does indium have? Indium is in group 3A. It's got 3 valence electrons. How about tin? Tin has 4. And arsenic? 5. So p-type semiconductor, we want to put something in there that has fewer valence electrons and is going to create some holes, and so that'll be indium. Any questions? What kind of a semiconductor would we get if we put arsenic in there? We get an N-type, because each arsenic atom has 5 valence electrons. That's 1 more than germanium has. And so that valence band's full, that extra electron has to go up into the conduction band. If you put tin in there, it's not going to really change anything.